What is actually happening with 3 Atlas? What if I told you that right now, at this very moment, something is flying past our sun that doesn't belong here? What if this object has travelled for millions of years through the cold darkness between stars, only to arrive at our cosmic doorstep in 2025? And what if everything about this visitor challenges what we thought we knew about comets, about our solar system, and about the universe beyond? What is actually happening with 3I Atlas? This is the question that has consumed astronomers, astrophysicists, and space enthusiasts around the world for months now. Because there is a very strange object flying past our sun. We don't exactly know what this thing is or what it's doing. We can't even see it anymore. But we have been watching this object very closely for months. We've given it a name, 3I Atlas, and we've given it a title, Interstellar Comet. But here's what makes this moment in history so extraordinary. We're witnessing something that happens incredibly rarely. In the entire span of human civilization, we've only confirmed 3 interstellar objects passing through our solar system. 3. And 3I Atlas is not just the third, it's the strangest, the fastest, and potentially the oldest thing we've ever tracked. There is a lot that we know about this new visitor to our solar system. In just 4 months, there have been nearly 100 research papers published on 3I Atlas, and there is plenty of other information out there that doesn't appear on the official record. Some of it can sound pretty insane. Theories range from the scientifically plausible to the wildly speculative. Social media has been flooded with questions. Is this a natural object? Could it be artificial? Why is it behaving so differently from anything we've seen before? So today we're going to cut through the noise and we're getting to the bottom of everything you actually need to know about 3I Atlas. We're going to explore its journey, its mysteries, and what it tells us about the vast universe beyond our small corner of space. Before we begin our journey, if you're kind enough, a gentle like or a quiet tap on subscribe would mean the world to me. It's a small gesture, but I hold it with deep gratitude because every bit of your support keeps this tiny universe alive and reminds me that these quiet stories still find their way to gentle hearts like yours. The current journey, perihelion and peak activity. Let's talk about the journey of this interstellar object. Right now, 3I Atlas is making its closest approach to the Sun. We call this phase perihelion, and the peak occurs on October 29th, when the object will pass within about 210 million kilometers of our star. Although in space we typically use a larger form of measurement, that's the astronomical unit or AU. 1 AU represents the average distance between the Earth and the Sun, approximately 150 million kilometers, which helps us to bring a familiar sense of scale to the vastness of the solar system. So the perihelion of 3I Atlas occurs at 1.4 astronomical units away from the Sun, which means it doesn't actually get that close. It's somewhere just inside the orbit of Mars. But this will be the time of peak activity for 3I Atlas. This is the hottest that it will get, which means that a lot of material from the surface of the object is going to get blasted out into space. Now, that's normal for a comet. We call this process sublimation. It's what happens when a solid material transitions directly into a gas because there's no liquid in the vacuum of space. The pressure is simply too low for liquids to exist in their conventional form. Sublimation is what gives a comet its distinct look with a fuzzy halo and a long tail. The halo is made of all the gas and dust being ejected from the hard surface of the object. It's technically known as the coma. The tail is created by solar wind. That's a name for the waves of radiation that constantly flow from the surface of the Sun. This wind blows back all of the lightest bits of dust and gas from the coma and pushes it away from the comet. It's a spectacular piece of cosmic ballet. The tail can stretch for millions of kilometers, always pointing away from the Sun regardless of which direction the comet is traveling. And unfortunately, we don't get to see this happening to 3i Atlas as it flies through its peak exposure to the sun because we are on the wrong side. Call it fate or call it something else. Our view of the perihelion is completely blocked out by the glare of the sun. The sun's brilliance overwhelms even our most powerful telescopes when an object passes too close to it from our perspective. It's like trying to spot a firefly next to a spotlight. During this hidden phase, astronomers estimate that 3i Atlas is releasing thousands of kilograms of material every second. The surface temperature of the comet facing the sun could be reaching several hundred degrees Celsius, while the side facing away remains frozen at temperatures hundreds of degrees below zero. This extreme temperature gradient creates intense pressure differences that drive the sublimation process even more vigorously. The discovery: when fast became too fast. Okay, so we know where 3i Atlas is right now, and we have a pretty good idea of what it's doing. So, while we wait for it to reappear on the other side, that gives us an opportunity to investigate how it got here in the first place. And this is a deeply fascinating story. We have been tracking 3i Atlas since July 2025. It was officially spotted by the Asteroid Terrestrial Impact Last Alert System, or ATLAS, which is actually a bunch of telescopes all around the world in places like Hawaii, Chile and South Africa. These telescopes work in coordination, creating a global network that can monitor the entire night sky. What they do is stare at the night sky and look for moving objects, and that is what they saw on the night of July 1st. Just another moving object. So they classify it as a new asteroid and they're ready to move on. But then they notice something weird about this one. It's moving too fast. And I mean really fast. Faster than anything that should naturally exist in our solar system. Everything in space is constantly in motion, and every object in the solar system rotates around the sun because we are all trapped by its force of gravity. The fact that we are moving is what keeps us from falling into the well of gravity. Think of it like a ball on a string. If you spin it fast enough, the centrifugal force keeps it from falling toward your hand. And the closer you get to the sun, the faster you have to move in order to stay afloat. But if you start to move fast enough, then you actually start to rise up out of the well. And if you reach a certain velocity, then you break free completely of the sun's gravity, and you can fly out into interstellar space. You enter the void of nothingness that exists between stars. This velocity is called escape velocity, and for our solar system, it varies depending on where you are. And when astronomers clocked the velocity of this new asteroid, they were shocked. This was the fastest moving object ever detected in our solar system. Let's establish some scale here. The planet Earth orbits the Sun at a speed of 30 kilometers per second. That's us. We're moving pretty fast and we're pretty close to the Sun, but there are planets that are a lot closer. Here is Mercury, 0.4 astronomical units from the surface of the Sun. It gets cooked, and to avoid falling into the gravity well, Mercury has to orbit at a velocity of around 48 kilometers per second. That's fast enough to circle the Earth's equator in about 14 minutes. The new object discovered by Atlas was moving at 58 kilometers per second, and at the time it was still way out there, just inside the orbit of Jupiter. That's about 4.5 AU away from the Sun, and at that speed it was clear that this object was going to blow straight past the Sun and just keep on going. We call this a hyperbolic trajectory, meaning that this thing had come from the void from interstellar space, and that's where it was going to return after completing its grand tour of our solar system. To put this in perspective, the fastest human-made object, the Parker Solar Probe, reaches speeds of about 92 kilometers per second at its closest approach to the Sun, but that's because it's deliberately diving into the Sun's gravity well. For a natural object to be travelling at 58 kilometers per second while still so far from the Sun meant it had an enormous amount of kinetic energy. energy that could only have been accumulated over an incredibly long journey through space. This is when the name 3I Atlas came to be, third interstellar object, which means there were two before it. The Interstellar Family, a tale of three visitors. You probably know this one. Oumuamua, the first ever identified interstellar visitor. It appeared in October 2017 and immediately captured the world's imagination. Oumuamua was weird in its own unique way. It had an elongated cigar-like shape, tumbled end over end through space, and exhibited a slight acceleration that couldn't be explained by outgassing alone. Some scientists proposed it might be a shard of a planet torn apart by tidal forces, while others suggested more exotic explanations. The object's unusual properties sparked debates that continue to this day, with some researchers proposing it could have been a piece of solid hydrogen ice, while others entertained the possibility of it being an artificial light sail from another civilization. And we also have a second interstellar object, the often overlooked middle child 2I Borisov, which was actually not that weird. Aside from the fact that it was interstellar, it basically just acted like a normal comet. Discovered in August 2019 by amateur astronomer Gennady Borisov, this object behaved exactly as we expected a comet to behave. It had water vapor, carbon monoxide, and familiar dust composition. It formed a normal coma and tail. In many ways, 2I Borisov was reassuring. It told us that some things in other solar systems were made from the same cosmic recipe as our own comets. So if anything, it was weirdly not weird. But that just made 3I Atlas's oddities stand out even more. The three key differences why 3I Atlas stands apart. There are three big differences between 3I Atlas and its interstellar siblings. One is size. It's literally much bigger. Oumuamua was up to 400 meters across, about the size of a large asteroid or 4 football fields end to end. Borisov was as wide as 1 kilometer, making it more comparable to typical comets in our solar system. But 3I Atlas could be up to 5.6 kilometers in width. That's enormous. To put it in perspective, that's wider than Mount Everest is tall. If this object were to somehow impact Earth, which it won't, its trajectory takes it nowhere near us, it would be an extinction-level event far worse than the asteroid that killed the dinosaurs. The size estimation comes from analysing how much light the object reflects and how bright its coma appears. However, there's still uncertainty in this measurement, because we can't distinguish the solid nucleus from the surrounding gas cloud with perfect precision. Some estimates put the nucleus at around 3 kilometers, while others suggest it could be even larger. 2 is speed. Atlas travels at about double the velocity of Oumuamua and Borisov. While those objects were moving at around 26 to 30 kilometers per second relative to the Sun, 3I Atlas blazes through at 58 kilometers per second. This higher velocity tells us something important about where it came from and how it was ejected from its home system. An object doesn't achieve that kind of speed by accident. It requires a powerful gravitational interaction, possibly a close encounter with a giant planet or even a stellar companion, and 3 is the direction that the object came from. And this is the really weird one. Oumuamua came in from above from the northern sky, which is the general direction that the solar system is moving. So we're all orbiting the Sun, but the Sun itself is also orbiting around the centre of the Milky Way galaxy, and it's dragging us along with it at a speed of about 220 kilometers per second. So as much as Oumuamua hit us, we also kind of ran into it, like a car driving into rain. 2I Borisov did mostly the same thing. Came in at more of a diagonal angle than straight on, but from the same general direction. This made sense statistically. If you're moving through space, you're more likely to encounter objects from the direction you're heading. Now, 3I Atlas is not another head-on collision. This one is a T-bone, and it's coming in on that side angle in almost perfect alignment with all of the planets. Our solar system is like a disk of stuff that all formed around the sun. Over time, all of that stuff kept smashing into each other and forming into planets and moons and asteroids and things, but it all remained in a relatively flat disk shape. We call that disk the plane of the ecliptic. There are only a few things that are a little bit offset from that plane. The most recognisable one would be Pluto. Its orbit is tilted by 17 degrees, so sometimes it's a little above the plane of the ecliptic and sometimes it's below. It's important to know that so we can appreciate how well aligned 3I Atlas actually is. The interstellar object is only 3 degrees off from that ecliptic plane. It hit our solar system in perfect alignment with the disk. Space is three-dimensional, and that object could have come from any direction. So to have something hit us almost perfectly side-on, it's a very big coincidence. The statistical probability of this alignment is quite low. Less than 5% of all possible trajectories would result in such a flat approach angle. Some astronomers have speculated that this alignment might not be entirely coincidental. The plane of the ecliptic is also roughly aligned with the plane of the Milky Way galaxy itself, so objects originating from certain regions of the galactic disk might naturally approach us at angles that match our own orbital plane. Still, the precision of this alignment is remarkable. Ancient origins, tracing a 7 billion year journey. But that leads us into an even bigger question. Where did 3I Atlas come from? Well, we know that it came from the direction of the galactic core, so if we look at the Milky Way galaxy from this usual top-down perspective, you are here in this kind of outer half of the galaxy, located in a spiral arm called the Orion Arm, or the Orion Spur. When you see the Milky Way in the night sky, that's the next spiral arm over, the Sagittarius Arm. Anyway, 3I Atlas came from the direction of this bright core in the middle. It's bright because it's full of stars and they're packed together much more tightly than the ones in our neighbourhood. In the galactic core, stars can be separated by as little as a few light weeks, compared to the 4.2 light years to our nearest stellar neighbour, Proxima Centauri. But again, space is three-dimensional, so to really understand where 3I Atlas originated, we need to flip the galaxy over to a side view, and just like our solar system, most of the stuff in the Milky Way is concentrated in a thin disk around the core. This thin disk is where most of the galaxy's stars are currently being born, where massive molecular clouds collapse to form new stellar systems, and where the spiral arms are most prominent. But also like our solar system, there are a few things that kind of hang out above and below the thin disk. In the galaxy, we call that area the thick disk. It's a lot less crowded in the thick disk, so you don't get nearly as many giant collisions and supernova explosions and black holes and stuff. So things in this region tend to just hang out undisturbed for very long periods of time. And that's where astronomers believe 3I Atlas came from. This ancient region of space, which could make it as old as 7.6 billion years, nearly twice the age of our own planet. To understand how ancient this is, consider that when 3I Atlas might have formed, Earth was still 3 billion years away from existing. The universe itself was only about 6 billion years old. The first complex life wouldn't appear on Earth for another 6 billion years. The thick disk of the galaxy is home to population 2 stars, older, metal-poor stars that formed when the universe was young and hadn't yet been enriched by many generations of supernovae. If 3I Atlas formed in a planetary system around one of these ancient stars, it would have a very different chemical composition than objects formed in younger systems like our own. Now, we'll probably never be able to trace the journey of 3I Atlas all the way back to its point of origin, but astronomers have recently managed to backtrack over 10 million years and they've identified 93 stars that the object would have encountered over that period. Using sophisticated computer simulations that account for the gravitational influences of stars and the motion of the galaxy itself, researchers have reconstructed the object's path through space. But what's deeply fascinating is that over the course of that 10 million years, the closest it would have come to any of those 93 other stars was a distance of 0.3 light years. That's 63,000 astronomical units. And right now, 3i Atlas is just 1.4 AU away from our own Sun. This means that 3i Atlas has been wandering through the deep void of interstellar space for at least 10 million years, possibly much longer, without experiencing any significant gravitational interaction with another star. This lonely journey through the darkness raises profound questions. What star system ejected it? Was it flung out by a close encounter with a giant planet? Or was its home star part of a binary system, and the gravitational dance of two suns eventually cast it into the void? We may never know, but the object itself carries clues written at its composition, clues we're only just beginning to read. The TESS discovery: first light and strange brightness. Now, let's talk a little bit more about how 3i Atlas approached the Sun and what we learned about it along the way. Even though 3i Atlas was officially discovered on July the 1st, it was actually spotted for the first time on May 7th, 2025. It showed up in images captured by the Transiting Exoplanet Survey Satellite, or TESS. It's an observatory that orbits the Earth and looks deep into the galaxy, trying to identify new planets in other star systems by detecting the tiny dips in starlight that occur when a planet passes in front of its host star. And for a period of about 1 month, TESS just happened to be looking in the direction of 3i Atlas. This gave us the opportunity to track the object as it moved through the orbit of Jupiter. The fact that TESS captured this object at all was somewhat fortuitous. The satellite wasn't designed to track fast-moving objects in our solar system, but the 27-day observation period was long enough for astronomers to notice something moving across the field of view. The first thing that astronomers wanted to measure was the object's brightness and how it changed over time. That's going to tell us about what this thing is made of. We know that in the 1-month period that 3i Atlas was observed by TESS, it travelled about 1 AU in the direction of the Sun, so we would expect it to get brighter over that time. This is basic physics. As an object gets closer to a light source, it receives more light and can reflect more light back to us. Astronomers use a term called flux to describe the perceived brightness of an object in space. Here's an example of how this works. Think about how bright the Sun appears from your location at noon on a clear day. Now, imagine you're transported to the surface of Mercury. That same Sun is going to suddenly appear a whole lot brighter, bright enough to incinerate you. The solar flux at Mercury's surface is about 7 times greater than on Earth. Now, the actual brightness of the Sun didn't change, only your perception of it. That is flux. It obeys the inverse square law. If you halve the distance, the flux increases by a factor of 4. So astronomers had a hypothesis that the flux of 3i Atlas would increase by a factor of 1.5 between May and June, based on its changing distance to the Sun. But data from TESS showed that the flux actually increased by a factor of 5, so there was a massive increase in the amount of light being reflected by this object, and that's how we know that this isn't an asteroid. Asteroids are bare rock or metal. Their brightness changes predictably with distance and rotation, but they don't suddenly become dramatically brighter unless something extraordinary happens. So, it must be a comet that's beginning to form its coma of gas and dust, which is what's reflecting all of that excess light. Only there are 2 weird things about this observation: the polarization mystery, light behaving backwards, One has to do with the polarization of light. Now this is a tough one to explain, so we're going to oversimplify here, but bear with me because this is important. When light from the sun hits that cloud of gas and dust around 3I Atlas, it's going to scatter in different directions, but the direction that the light bounces is not random. It can tell us a lot about the material that the light is hitting, specifically the size, shape and composition of the particles. If the light scatters off to the side at a right angle or perpendicular, then we call that positive polarization. If the light bounces straight back in a parallel direction, then we call that negative polarization. Most objects in space have a positive polarization, even interstellar objects. 2A Borisov was positive, consistent with the silicate dust and ice particles we expected. But 3 Atlas is negative, and not only that, it has the most extreme negative polarization of any object ever discovered. The degree of negative polarization measured from 3I Atlas exceeds 40% at certain angles, which is almost unheard of. That's pretty weird. And it's just one of the many oddities about 3I Atlas that tells us not all solar systems are the same. What we think is normal here would be weird somewhere else, and what's normal in a different star system is considered weird around here. Negative polarization typically indicates that the scattering particles are either very small, comparable to the wavelength of visible light, or have a very specific refractive index. Some researchers have proposed that the coma of 3I Atlas might contain unusual carbon compounds or organic molecules that we don't commonly see in solar system comets. Others suggest the particles might be coated with organic material, creating a structure that scatters light in unexpected ways. This polarization signature might also tell us about the conditions in the planetary system where 3I Atlas formed. Different temperatures, pressures, and chemical environments produce different types of dust and ice. The fact that 3I Atlas has such unusual optical properties suggests it formed under conditions quite different from those in our own solar system. The early coma, waking up in the cold. And then the second surprising thing about the coma of 3I Atlas was the fact that it even existed at all. Remember, we're looking at this period between May and June, and 3I Atlas is still way out there beyond the orbit of Jupiter. This is over 5 AU away from the Sun. It's cold out there, really cold. The temperature at this distance is around 150 degrees Celsius or about 123 Kelvin. It's so cold that we don't typically spot comets at 5 AU because they typically have not begun to form their coma yet. They're still frozen solid. It's not usually until somewhere between 3 and 4 AU that the sublimation process really kicks in. And that's because typical comets from our solar system are typically made of water ice, which needs a lot of energy to melt. Water ice doesn't sublimate significantly until temperatures reach around 70 degrees Celsius. That's why the frost line or snow line in the early solar system, the boundary beyond which water could remain frozen, was located around 3 AU from the Sun. Inside this line, water evaporated. Outside it, water froze into ice. But as we continued to observe 3I Atlas, and we started pointing our most powerful telescopes directly at it, we learned that the coma was actually dominated by CO2 gas. It did have some water vapour, but the ratio of CO2 was much higher at around 8.1. That's basically the opposite or inverse of what we are used to finding in comets. If you've ever seen dry ice before, it's typically used to create a smoky effect for live performances. That's frozen CO2. It has to be created and stored at incredibly cold temperatures, around 78 degrees Celsius, or 195 Kelvin at normal atmospheric pressure. And as soon as it's removed from the deep freeze, dry ice will instantly begin to sublimate, making that signature cloud of gas. That is what 3I Atlas was doing way out there in space, and that's why its coma formed so early, because CO2 ice melts at a much lower temperature than water ice. In the vacuum of space, CO2 can sublimate at temperatures as low as 125 degrees Celsius, which explains why 3I Atlas began outgassing so far from the Sun. This high CO2 content tells us something profound about the formation environment of 3I Atlas. In our solar system, comets typically form with more water than CO2 because water was more abundant in the planet-forming disk. But in colder regions, or in systems with different chemical compositions, CO2 can dominate. Some astronomers speculate that 3I Atlas might have formed in the outer regions of its home system, beyond the equivalent of our Kuiper belt, where CO2 ices would be more stable. The water eruption, a fire hose in space. And we've continued to observe 3I Atlas on its approach to the Sun. We've seen that ratio of CO2 and water begin to flip. By late in September, as it was passing through the orbit of Mars at just over 1.5 AU, the object had actually begun to release a massive amount of water vapour, about the equivalent of a fire hose running at full blast, which is actually more water than we would expect, even from a normal comet at this distance. To be more specific, astronomers measured the water production rate at approximately 1,000 to 2,000 kilograms per second during this period. That's equivalent to filling an Olympic-sized swimming pool every hour. For comparison, Comet Hale-Bopp, one of the most active comets in recent history, was producing about 300 kilograms of water per second at a similar distance. We've never seen so much water vapour appear so suddenly. The onset of water, sublimation was abrupt and intense, suggesting that the comet's structure might be layered, with a CO2-rich outer layer giving way to a water-rich interior. When the outer layers sublimate away, they expose the deeper ice to solar radiation, triggering this explosive release of water vapour. This sudden transition raises interesting questions about the internal structure of 3I Atlas. Is it a homogeneous ball of ice? Or does it have distinct layers formed during different epochs of its formation? The rapid increase in water production suggests the latter, that this comet has a complex internal structure that's being revealed layer by layer as it approaches the Sun. The metal mystery, iron and nickel in the void. The same thing can be said for metal in the coma of 3I Atlas. When it was observed over the summer, astronomers detected a small amount of nickel in the surrounding cloud, but they did not detect any iron. So, a couple of things to note here. One is that nickel and iron are pretty common in the universe because they are formed inside the core of a dying star. When a massive star reaches the end of its life, its core undergoes nuclear fusion, creating heavier and heavier elements in a process called nucleosynthesis. Iron and nickel are the final products of this process, the most stable elements that can be created through fusion. Then that star goes supernova and blasts these metals out into the surrounding area of space, where it gets pulled in by new stars that are beginning to form their own planetary disk. And then the process repeats. So because nickel and iron come from the same place, they're typically found together in planets, moons, asteroids, and comets. In our solar system, the nickel to iron ratio is fairly consistent across different bodies, roughly 120 by mass. This ratio reflects the abundances created by stellar nucleosynthesis, and hasn't changed significantly since the solar system formed. So when we see a lot of nickel, but no iron, we wonder where the iron went. What process separated them? Did 3I Atlas form in a chemically unusual environment? Or has it undergone some kind of processing during its journey through space that preferentially removed iron? And thing number 2, it's weird to see any metal at all sublimating from 3I Atlas given its distance to the Sun when this observation was made. It's still way out beyond Mars in the region of the asteroid belt, which is still very cold, and the process of sublimation is driven by heat. Now, when it comes to CO2, We know that it doesn't need much heat in order to melt, but when we're talking about metal, there's something else going on. Metals have extremely high sublimation temperatures. Iron doesn't even begin to sublimate until temperatures exceed 1,500 degrees Celsius. Clearly, the surface of 3I Atlas isn't anywhere near that hot at 5 AU from the Sun. Likely, the massive release of CO2 is dragging nickel atoms along with it. This is called entrainment. Small particles of metal embedded in the ice get carried away by the outrushing gas. But that still doesn't account for the iron deficiency. Why would CO2 preferentially carry nickel over iron? One possibility is that the nickel exists as very fine dust particles, or even as nanometer scale grains that are more easily lifted by gas pressure, while iron might be present as larger grains that remain on the comet's surface. Another hypothesis suggests that the nickel might be chemically bound to organic molecules or carbon compounds in a way that iron is not, making it more volatile. Now, just like water vapour made a very sudden appearance in the coma of 3I Atlas, the same thing did eventually happen with iron. By late into September, astronomers had started to detect iron for the first time in the coma, and then very quickly, the ratio of nickel to iron changed to a more normal combination of the two. So 3I Atlas is becoming more normal over time, but it's getting there in a very strange way. It's as if the comet is revealing itself in stages, each layer having a different composition and producing different outgassing behaviour. This evolutionary pattern gives us a window into the internal structure of the object, a structure built over billions of years in a star system far from here. The detection of metals in cometary comae isn't entirely unusual. We've detected iron, nickel, sodium, magnesium, and other elements in various comets. But the sequence and abundance ratios in 3I Atlas are unlike anything we've seen before, once again reinforcing that this visitor comes from a very different cosmic neighbourhood. The backward tail, defying solar wind. Now, let's talk about tails. This is another area where 3I Atlas has behaved a little different from your average comet, and that's mostly because the first time we saw a tail forming around 3I Atlas back in the summer, it was pointing in the wrong direction. This object initially formed a sun-facing tail. Let that sink in for a moment. The tail was pointing toward the sun, not away from it. This is unusual because the tail is considered to be an effect of the solar wind interacting with the coma. The solar wind blows away from the sun at speeds of 400 to 800 kilometers per second, carrying charged particles and magnetic fields, so therefore we expect the tail to flow in that direction, away from the sun. In this case it didn't, which could be related to the early formation of the coma, which was due to the high CO2 concentration. Because the object began sublimating at a very long distance from the sun, it's possible that the solar wind just wasn't strong enough yet to push the cloud of gas and dust away. The solar wind decreases in intensity with distance from the sun. By the time you reach Jupiter's orbit at 5 AU, the solar wind pressure has dropped to about 4% of its strength at Earth's orbit. So when 3I Atlas first began producing its coma, the outward pressure from sublimation might have been stronger than the inward directed solar wind pressure at that location. So what we saw was more of that cloud accumulating on the warm side of the object, the sun-facing side, before it encountered a strong enough wind to form a conventional tail. The sun-facing side receives more solar radiation, which drives more intense sublimation. Without sufficient solar wind to blow this material away, it simply accumulated as a forward-pointing protrusion, a tail that defied our expectations. This forward tail persisted for several weeks, baffling observers and generating extensive discussion in the astronomical community. Some researchers proposed alternative explanations, including the possibility that we were seeing jets of material being expelled from active regions on the comet's surface that happened to be oriented toward the sun. which is what 3i Atlas eventually did. By September, a short fan-shaped tail facing away from the sun developed, which is pretty normal. Not all comets have long streaking tails like what we're used to seeing in illustrations. The length of the tail varies according to what the comet is made of and its distance to the sun. For example, Comet Hale-Bopp is pretty famous for having a gigantic tail when it was observed in 1997. Actually, it had two distinct tails. A blue ion tail made of charged gas particles, and a white dust tail made of larger solid particles. At its peak, these tails stretched over 100 million kilometers across the sky, visible to the naked eye even from light-polluted cities. But it was also very close to the Sun at that time, about 0.9 AU, half of an AU closer than 3i Atlas will ever get to the Sun. So of course, it experienced more sublimation and solar wind, which shaped that tail. The closer proximity meant higher temperatures, more outgassing, and stronger solar wind pressure, all factors that contribute to impressive tail development. The tail of 3i Atlas, by contrast, remains relatively modest. It's visible in telescopic images as a diffuse, fan-shaped feature extending several 100,000 kilometers from the nucleus, but it's nothing like the spectacular displays of Hale-Bopp or other famous comets. This is partly due to its greater distance from the Sun, and partly due to its composition. The type and amount of material being released simply doesn't create the dramatic visual display we sometimes associate with comets. The Mars Encounter, our closest look. And it's around this time that we actually get our closest possible observation of 3i Atlas, but the view doesn't come from the Earth, it comes from Mars. On October 3rd, the object passes within 0.19 AU of the planet Mars, the closest it will come to any planet in the solar system. That's about 28 million kilometers. Still an enormous distance, but in astronomical terms it's practically a close encounter. And this is lucky for us because we have a lot of cameras on and around the red planet, which means we were able to use them to image 3i Atlas. Currently there are multiple active missions at Mars: the Perseverance and Curiosity rovers on the surface, the Ingenuity helicopter, the Mars Reconnaissance Orbiter, the Maven Orbiter, the European Space Agency's Mars Express, and ExoMars Trace Gas Orbiter, and others. This flotilla of scientific instruments gave us an unprecedented opportunity to observe an interstellar object from multiple perspectives. Here is a photograph taken by the Perseverance rover from the surface of Mars. This is how the object would have appeared in the night sky to anyone standing on the Martian surface. It's not a great picture. This isn't what the rover's camera was designed for. Perseverance's cameras are optimized for studying rocks, soil, and the Martian landscape, not for deep sky astrophotography. And in order to see this much light, the camera had to take 30-second long exposures. Then several of those images were stacked on top of each other to increase the signal-to-noise ratio and bring out fainter details. So what you end up with is more like a streak than a defined object. Because the rover itself is stationary, but the comet is moving rapidly across the sky, each exposure captures the comet in a slightly different position, creating a trail of light. Still, the fact that Perseverance could image 3i Atlas at all is remarkable. The comet appeared as a faint smudge in the Martian sky, barely visible even with long exposures. For any hypothetical future colonists on Mars, 3i Atlas would have been a naked eye object, faint but visible, a cosmic visitor passing by their new home. And here is another image of 3i Atlas taken by the European Space Agency's ExoMars Trace Gas Orbiter, which hangs out in orbit around Mars. We can see the object a little more clearly now, but there's still not enough resolution to distinguish between the bright coma and the surface of the object itself. The coma appears as a diffuse glowing cloud, brightest at the centre where the nucleus resides, but gradually fading as you move outward. The ExoMars orbiter captured multiple images over several days, allowing astronomers to track the comet's motion and measure changes in its brightness and coma structure. These observations revealed subtle variations in the outgassing rate, possibly indicating that the nucleus is rotating and exposing different surface features to sunlight. In order to get that fine detail, we would need to take a photo with NASA's Mars Reconnaissance Orbiter, which has the most powerful telescope in the Mars system. The HiRISE, High Resolution Imaging Science Experiment camera on this orbiter is capable of resolving features as small as 30 centimeters across on the Martian surface. If turned toward 3I Atlas, it could potentially resolve details in the coma structure and might even distinguish the nucleus from the surrounding gas cloud. Unfortunately, at the time we are making this video, that image has not been released, if it was even taken at all. Basically, there's been a shutdown of the US government, and people at NASA aren't going to work until some political stuff gets resolved, which unfortunately could take some time. Many scientists and mission controllers have been furloughed, and non-essential operations have been suspended. The timing is frustrating for the scientific community, as this was a once-in-a-lifetime opportunity to observe an interstellar object from Mars. The waiting game, hidden by the sun. But time is something that we have right now because the sun is going to continue blocking our view of 3I Atlas until early December, at which point we'll be able to study the effect that the sun had on the object. During this occlusion period, which lasts approximately 6 weeks, the comet is essentially invisible to us. It's on the far side of the sun from Earth's perspective, and the sun's overwhelming brightness makes observation impossible. This is one of the most frustrating aspects of astronomy. Sometimes the universe doesn't cooperate with our observational schedules. Despite our sophisticated technology and global network of telescopes, there are still fundamental limitations imposed by celestial mechanics. We can calculate exactly where 3I Atlas is during this period. We can model what should be happening to it, but we can't actually see it. What we do know is that during perihelion on October 29th, 3C Atlas experienced its peak solar heating. The surface temperature on the sun-facing side likely exceeded 200 degrees Celsius, while the night side remained frozen at temperatures below 200 degrees Celsius. This extreme temperature gradient creates enormous thermal stress on the nucleus, potentially causing it to fracture or fragment. Cometary fragmentation is not uncommon. Comet Shoemaker-Levy 9 famously broke into more than 20 pieces before colliding with Jupiter in 1994. Comet 73P Schwarzmann-Wachmann 3 has been observed breaking apart during multiple apparitions. If 3I Atlas were to fragment during perihelion, we wouldn't know until it re-emerges from behind the sun. During this hidden period, the water production rate likely increased dramatically, possibly reaching 10,000 kilograms per second or more at peak heating. The coma would have expanded significantly, potentially reaching a diameter of several 100,000 kilometers. The tail, pushed by increasingly strong solar wind, would have lengthened and become more defined. Although the closest that we'll get is still 1.4 AU, that happens on December 19th. At this point, 3C Atlas will be well on its way out of the solar system, cooling down as it recedes from the sun. The sublimation rate will decrease, the coma will begin to dissipate, and the comet will gradually return to its frozen dormant state, though it will never be quite the same as it was before entering our solar system. When 3I Atlas re-emerges from behind the sun in early December, astronomers will be watching intently. They'll measure its brightness to see if it survived perihelion intact. They'll analyze the composition of its coma to see what new materials might have been exposed. They'll track its rotation to see if thermal stress has changed its spin rate. Every observation will add another piece to the puzzle of what this object is and where it came from. The Jupiter finale, one last glimpse. But there is just one more close encounter still to come. On March 16th, 2026, the object will fly within 0.36 AU of Jupiter. That's about 54 million kilometers, not particularly close by solar system standards, but close enough for Jupiter's gravity to have a measurable effect on the comet's trajectory. While we don't have nearly as many cameras around Jupiter as we do at Mars, we do have one. It's on a probe called Juno, which has spent the past decade observing the gas giant and its moons. Juno arrived at Jupiter in July 2016 and has been in a highly elliptical polar orbit ever since, diving close to the planet's cloud tops every 53 days to study its atmosphere, magnetic field, and internal structure. But it will have a chance to take one last image of 3I Atlas before it disappears. Juno's JunoCam, while primarily designed for public outreach rather than scientific observation, has proven capable of capturing stunning images of Jupiter's atmosphere and has occasionally been turned toward other targets of opportunity. If mission planners decide to point JunoCam at 3I Atlas, we might get one final view of this interstellar traveller. Now, at this distance, the object will be cooling down. It's going to be less active. By the time it reaches Jupiter, 3I Atlas will be approximately 2.5 AU from the Sun, well beyond the region where water ice sublimates readily. The coma will have contracted significantly, and the tail may have faded to near invisibility. The comet will be returning to its dormant state, the state it maintained for millions of years during its journey through interstellar space. But it could be changed by its exposure to the Sun, and that will add an extra layer of understanding to these interstellar objects. Every time a comet passes close to the Sun, it loses mass, sometimes a few million tons, sometimes much more. This mass loss erodes the surface, exposing fresh material beneath. For 3I Atlas, this passage through the inner solar system represents a transformation, a shedding of its outer layers to reveal what lies within. It's entirely possible that a lot of these strange characteristics didn't even come from the place where the object was formed. It's just an accumulation of weird stuff that it picked up along the way. During its millions of years wandering through interstellar space, 3I Atlas was exposed to cosmic rays, interstellar dust, and the harsh radiation environment between the stars. Material from the interstellar medium might have slowly accumulated on its surface, coating it with a thin layer of alien chemistry. Some researchers have proposed that interstellar objects might act as vectors for panspermia, the transfer of life or organic molecules between star systems. While there's no evidence that 3I Atlas carries any biological material, it almost certainly contains complex organic molecules formed in its home system. These molecules could provide clues about the chemistry of planet formation in other solar systems and the diversity of organic compounds in the galaxy. What we've learned, rewriting the textbooks. For now, we can only wonder, but more answers and probably more questions are soon to come. What has 3I Atlas taught us so far? What fundamental insights have we gained from this cosmic visitor? First, it has shown us that interstellar objects come in many varieties. The sample size is small, just 3 confirmed objects, but already we've seen enormous diversity. Oumuamua's elongated shape and mysterious acceleration, Tui Borisov's familiar comet-like behaviour, and now 3I Atlas with its extreme speed, unusual composition, and bizarre optical properties. If these 3 objects are representative of the broader population of interstellar travellers, then the galaxy contains an incredibly diverse array of planetary building blocks. Second, it has revealed that not all comets are created equal. The chemistry of 3I Atlas dominated by CO2 rather than water, with unusual metal abundances and extreme negative polarization, tells us that planetary systems form under wildly different conditions. Temperature, pressure, radiation, environment, and the chemical composition of the parent molecular cloud all influence what kinds of objects form. 3I Atlas is a messenger from a very different cosmic environment, carrying information about the conditions in a star system billions of years old. Third, it has demonstrated the importance of being ready. The discovery of 3I Atlas was only possible because we had automated sky survey systems like Atlas operating continuously. The detailed follow-up observations were only possible because we have a global network of telescopes that can be rapidly redirected to new targets. And the close-up observations from Mars were only possible because we happen to have multiple spacecraft there at the right time. This raises an important question. How many interstellar objects have we missed? Before Oumuamua, we didn't even know to look for them. Now that we know they exist, we found 3 in just 8 years. Statistical studies suggest that at any given moment, there might be dozens or even hundreds of interstellar objects passing through the inner solar system, most too faint to detect. Projects like the Vera C. Rubin Observatory's Legacy Survey of Space and Time, LSST, which is expected to begin operations soon, will dramatically increase our ability to detect these objects. LSST will survey the entire visible sky every few nights, detecting objects far fainter than current surveys can see. Some estimates suggest it might detect 1 interstellar object per month once it's fully operational. The bigger picture, a galaxy. Full of wanderers. Fourth, 3I Atlas has given us a glimpse into the violent dynamics of planetary system formation and evolution. For an object to achieve escape velocity from its home star system, something dramatic must have happened. Perhaps a giant planet in a highly elliptical orbit gravitationally scattered smaller objects, flinging some into interstellar space. Perhaps the system contained binary stars, and the complex gravitational dance between 2 suns ejected material from the system. Perhaps a close encounter with another star disturbed the system's stability. Whatever the mechanism, the very existence of interstellar objects tells us that planetary systems are not static, peaceful places. They're dynamic, chaotic environments where gravitational interactions can eject objects into the galaxy-wide void. Our own solar system has almost certainly contributed to this population. Jupiter and the other giant planets have likely scattered countless comets into interstellar space over the past 4.6 billion years. This means that the galaxy contains a vast population of homeless worlds, planets, moons, asteroids and comets that no longer orbit any star. They drift through the darkness, occasionally passing through other planetary systems like ours, silent witnesses to the violence of their birth and ejection. Fifth, the alignment of 3I Atlas with the ecliptic plane raises intriguing questions about the structure of the galaxy itself. The fact that it approached us almost perfectly in the plane of our solar system might not be entirely coincidental. The Milky Way's galactic disk has its own structure, with most matter concentrated in a relatively thin plane. Objects originating from the galactic disk might naturally approach us at certain preferred angles. This could mean that the population of interstellar objects is not randomly distributed in 3-dimensional space, but has its own structure reflecting the larger scale organization of the galaxy. Understanding this distribution could tell us about the dynamics of the entire galaxy, how matter moves through it, how stars interact with each other, and how material is exchanged between different regions. The composition mystery. What is 3I Atlas made of? Let's dive deeper into one of the most puzzling aspects of 3I Atlas, its composition. We've touched on the CO2 dominance, the unusual metal ratios, and the strange polarization properties, but what does all of this actually tell us about what this object is made of? Spectroscopic analysis, breaking down the light from 3I Atlas into its component wavelengths, has revealed a complex mixture of materials. Beyond CO2 and water, astronomers have detected carbon monoxide, CO, present in smaller amounts than CO2, but still significant. CO sublimits at even lower temperatures than CO2, which means it comes from the coldest, most pristine regions of the comet. Ammonia, NH3, detected in trace amounts. Ammonia is important because it's a key ingredient in the chemistry of life. Its presence suggests that nitrogen-rich compounds were available in the system where 3I Atlas formed. Methane, CH4, also in trace amounts. Methane is common in the outer solar system but usually frozen solid at cometary distances. Hydrogen cyanide, HCN, an organic molecule that's crucial for prebiotic chemistry. Its presence indicates that complex carbon chemistry was occurring in the formation environment. Silicate dust, the mineral particles that give the coma some of its brightness. Spectral analysis suggests the silicates might be slightly different in composition from those system comets, possibly indicating different formation temperatures or pressure conditions. Organic polymers, complex long-chain carbon molecules that might give the dust grains their unusual optical properties. These could be similar to tholins, the reddish-brown organic compounds found on bodies like Pluto and Saturn's moon Titan. This chemical inventory paints a picture of an object formed in a cold, carbon-rich environment, possibly in the outer reaches of its home planetary system. The high CO2-water ratio suggests formation temperatures around 30-50 Kelvin, colder than the region where most of our solar system's comets formed. The nucleus, what lies beneath? What about the nucleus itself, the solid body at the heart of the coma? We still don't have a clear image of it, but we can infer some of its properties. Size estimates based on brightness and thermal emission suggest a nucleus diameter between 3 and 5.6 kilometers. This makes it larger than most cometary nuclei we've studied up close. For comparison, Comet 67P, Churyumov-Gerasimenko, visited by the Rosetta mission, has a nucleus about 4 kilometers across. The nucleus is likely irregular in shape, as most comet nuclei are. They're not smooth spheres, but lumpy potato-shaped objects with hills, valleys, and cliffs. The rotation period, the time it takes to spin once on its axis, appears to be around 8 to 10 hours based on variations in brightness, though this measurement is uncertain. The surface is probably covered with a dark, non-volatile crust, formed by the gradual accumulation of material that doesn't sublimate. This crust acts as an insulator, slowing the loss of ice from the interior. When active regions on the surface are heated by the sun, the ice beneath the crust sublimates, building up pressure until it breaks through, creating jets of gas and dust. The density of the nucleus is probably quite low, perhaps 300-600 kilograms per cubic meter, about half the density of water. This suggests a porous, fluffy structure with lots of empty space between ice grains and dust particles. Some models propose that comet nuclei are rubble piles, loosely held together by gravity and ice rather than solid chunks of material. The trajectory, past, present, and future. Let's talk more precisely about the path 3I Atlas has taken and will take. When it entered the solar system, it was moving at 58 kilometers per second relative to the Sun. As it fell deeper into the Sun's gravity well, it accelerated, reaching a maximum speed of about 62 kilometers per second near perihelion. Now, as it climbs back out of the gravity well, it's slowing down again. By the time it crosses Jupiter's orbit outbound, it will have decelerated back to around 58 kilometers per second. This is still well above escape velocity, so it will keep going, out past the Kuiper belt, past the heliopause where the solar wind gives way to interstellar space, and back into the galactic void. The trajectory is hyperbolic, meaning it's not bound to the Sun. The specific orbital energy is positive, indicating the object has more than enough kinetic energy to escape the Sun's gravity. The eccentricity of the orbit is approximately 3.5. Anything above 1.0 indicates a hyperbolic, unbound trajectory. Where will it go next? Based on its outbound velocity and direction, astronomers have projected its future path. In about 10,000 years, it will have travelled about 1 light-year from the Sun. In 100,000 years, it will be 10 light-years away, possibly approaching another star system. In 1,000,000 years, it will have crossed a significant fraction of the distance between major spiral arms. Its journey will continue for billions of years, wandering through the galaxy, occasionally passing near other stars, perhaps even entering other planetary systems. Each encounter might subtly alter its trajectory, sending it in new directions. It's possible that millions of years from now, creatures on a planet orbiting a distant star will look up at their sky and see 3I Atlas passing through, just as we're seeing it now. The detection revolution, finding more visitors. The detection of 3I Atlas represents a triumph of modern astronomy, but it also highlights how much we've been missing. The universe is almost certainly full of these interstellar wanderers, but until recently we had no way to detect them. What changed? Several factors. 1. Automated survey telescopes, systems like ATLAS, Pan-STARRS, and the Catalina Sky Survey continuously scan the sky, taking thousands of images per night. Computer algorithms automatically compare new images with reference images, flagging anything that moves or changes brightness. 2. Improved computational power. The amount of data generated by modern sky surveys is staggering, tens of terabytes per night. Processing this data to find rare, fast-moving objects requires significant computing resources that simply weren't available a decade ago. 3. Better understanding of what to look for. Before Oumuamua, we didn't have clear criteria for identifying interstellar objects. Now we know to look for objects moving faster than escape velocity, with hyperbolic trajectories, approaching from unusual angles. 4. International coordination when Atlas detected 3I Atlas. The discovery was immediately shared with the global astronomical community. Within hours, telescopes around the world were pointed at the object, gathering data from multiple wavelengths and perspectives. The future looks even brighter. The Vera C. Rubin Observatory, with its 8.4-meter mirror and enormous field of view, will begin operations soon. It's expected to detect interstellar objects so frequently that they'll become almost routine, perhaps one per week during peak observing seasons. This raises an exciting possibility. We might be able to launch a mission to one of these objects. The European Space Agency's Comet Interceptor mission, currently in development, is designed to be placed in a parking orbit, waiting for a suitable target to be discovered. When a promising interstellar object is detected, the spacecraft could be redirected to intercept it, potentially giving us our first close-up images of an object from another star system. The speculation: could it be artificial? No discussion of interstellar objects would be complete without addressing the speculation that inevitably arises. Could 3I Atlas be artificial? Could it be a spacecraft, a probe, or some other technological artifact from an alien civilization? Let's be clear, there is no evidence to support this hypothesis. 3I Atlas behaves exactly as we would expect a natural comet to behave, with the exception of the unusual compositional features we've discussed. But unusual doesn't mean artificial, it just means different from what we're used to seeing in our own solar system. That said, the speculation isn't entirely unfounded. Oumuamua's strange acceleration sparked serious scientific discussion about whether it could be an artificial light sail, with at least one peer-reviewed paper exploring this possibility. The idea was ultimately deemed unlikely, but the fact that it was seriously considered shows that scientists are keeping an open mind. For 3I Atlas, there are no anomalous accelerations or other behaviours that can't be explained by natural processes. The high CO2 content, unusual metal ratios and negative polarisation are strange, but they're the kinds of strange we might expect from an object formed under different conditions than those in our solar system. If we wanted to determine whether 3I Atlas was artificial, what would we look for? Some possibilities. Regular geometric shapes. Natural objects are irregular. Artificial ones might show symmetry. Radio emissions. A functioning probe might emit radio signals. Non-gravitational accelerations. Changes in velocity not explained by gravity or outgassing. Unusual thermal signatures. Artificial power sources might create heat patterns different from solar heating. None of these have been observed. 3I Atlas appears to be exactly what it seems, a very old, very fast comet from another star system. But the speculation serves a useful purpose. It reminds us to stay curious, to question our assumptions, and to remain open to unexpected discoveries. The universe has surprised us before and will certainly surprise us again. The science to come, unanswered questions. As 3R Atlas continues its journey through our solar system, several key questions remain unanswered. 1. Will it survive perihelion intact? Some comets fragment when heated by the sun. When 3I Atlas emerges from behind the sun in December, will it still be a single object, or will it have broken into multiple pieces? 2. What is its exact size and shape? We still don't have a clear image of the nucleus. The Mars Reconnaissance Orbiter data, if it's ever released, might help answer this question. 3. What is its internal structure? Is it a solid body, a rubble pile, or something in between? The pattern of outgassing as different layers are exposed might provide clues. 4. What is its rotation rate and spin axis orientation? This affects how evenly the surface is heated and could explain some of the variable outgassing behaviour. 5. Will Jupiter's gravity measurably alter its trajectory? While the flyby is relatively distant, Jupiter's immense mass might still have a small effect, slightly changing the comet's speed or direction. 6. What other trace compounds are present in the coma? More detailed spectroscopic analysis might reveal additional organic molecules or rare isotopes that tell us about the formation environment. 7. Is there any evidence of past activity? Did 3I Atlas pass close to other stars during its journey, causing previous episodes of sublimation? Or has it remained frozen and dormant for billions of years until now? These questions will keep astronomers busy for years to come. Even after 3I Atlas has departed, researchers will continue analysing the data, refining models, and publishing new discoveries. The legacy. What 3I Atlas teaches us. When all is said and done, what will 3I Atlas's legacy be? What will we remember about this interstellar visitor? Perhaps most importantly, it has expanded our understanding of what's possible. Every measurement that defied expectations, every unusual characteristic, every moment of surprise, these are teaching us that the universe is more diverse, more complex, and more interesting than we imagined. It has shown us that planetary systems throughout the galaxy create an enormous variety of objects, each carrying the chemical signature of its birthplace. By studying these interstellar travelers, we're essentially doing comparative planetology on a galactic scale, learning about planet formation not just in our own backyard but throughout the Milky Way. It has reminded us of our place in the cosmos. We're not isolated. Our solar system is part of a larger galactic ecosystem, with material being exchanged between star systems. The atoms in 3i Atlas were forged in a star that died billions of years ago, perhaps even before our sun was born. Those atoms formed a comet, wandered through space for eons, and now pass briefly through our neighbourhood before continuing their endless journey. It has demonstrated the power of preparation meeting opportunity. Because we had the right instruments in the right places, operated by dedicated teams of scientists and engineers, we were able to capture this fleeting moment. 3i Atlas will never return. Its trajectory will carry it away forever. But we were here, we were watching, and we recorded what we saw. Conclusion. The journey continues. As I write this, 3i Atlas is somewhere behind the sun, hidden from our view, experiencing the most intense heating of its multi-billion-year existence. Thousands of kilograms of ancient ice are being transformed into gas and blown away into space. The object that emerges on the other side will be fundamentally changed, lighter, with fresh layers exposed to the vacuum of space. In a few weeks, it will reappear, and telescopes around the world will turn toward it once more. Astronomers will measure, analyze, and marvel at what they find. More papers will be published, more data will be collected, and our understanding will deepen. By March 2026, after its Jupiter encounter, Thrushorska Atlas will be fading from view, too distant and too faint for most telescopes to track. It will cross the orbit of Saturn, then Uranus, then Neptune, each crossing taking it further from the warmth of our sun and back into the cold darkness it has known for most of its existence. By 2030, it will be beyond the Kuiper Belt. By 2050, it will be approaching the heliopause. By 2100, it will be in interstellar space once more. Its brief encounter with our solar system nothing but a warm memory encoded in the slight erosion of its surface. And we will be here, looking up at the stars, knowing that somewhere out there in the darkness, 3i Atlas continues its journey. It came from the void, passed through our cosmic neighbourhood, and returned to the void. But for a few precious months, we shared the same space, and in that sharing, we learned something profound about the universe and our place in it. What is actually happening with 3i Atlas? It's teaching us. It's showing us. It's reminding us that the cosmos is vast, ancient, and full of wonders we're only beginning to understand. And perhaps thousands or millions of years from now, when 3 Atlas passes through another planetary system around another star, intelligent beings there will look up, see this strange visitor, and wonder, just as we have wondered, where it came from, what it's made of, and what secrets it carries from the distant reaches of space. The journey continues, the questions multiply, and we watch, and we learn, and we marvel at the magnificent complexity of the universe we call home.